So I added problems on Wednesday, and I'm going to add some more problems today, and your homework will be due on Monday. Is what usual the schedule? The schedule is quite unusual. Usually usually finals are like at the end of the first week of December, but things have been pushed forward and compressed due to COVID, essentially. So the schedule is unusual. So no one well, actually that's not true. One person thus far has reached out to me about their exams. Yes, if you have specific questions on homework, office hours and email are a great place to do that. I'm very happy to meet in office hours or even have extra office hours to chat about homework problems. And the same goes for discussing your midterms. So I'm very happy to discuss midterms, but I usually don't plan on sending out like a answer sheet. So the thing that I want to provide is I really want to have discussions with y'all about the tests. I think that's a much more fruitful thing than just having an answer key. So if you have any sort of question whatsoever about your test, please send me an email and we can find a time to discuss it together. I think that's a much more helpful way to go over that material. Any questions before we continue? Okay, cool. So let's see. I want to kind of briefly summarize what we did in section 1.7. Essentially in 1.7, we found all of the building blocks for our proof strategies. So the building blocks for proofs are direct proof, contrapositive, contradiction, and then also vacuous proofs, trivial proofs, and then we also learned how to prove by implications or showing collections of statements are equal. Equivalent. Okay. So essentially, this is the material that we covered in 1.7, and especially these three are kind of the basic building blocks for a lot of the proofs that we're going to do. So moving into 1.8, we start developing, or 1.8 is kind of moving us into a slightly more creative side of proofs. So 1.8 is kind of more proof techniques, and proof strategy, and common types of proofs. And by common types, I mean showing something exists, or uniqueness of some object. So we won't get all the way through 1.8. So if you read through 1.8, about halfway through, they start going into things like chomp and tilings and things like that. We won't get into those. So if you want to be reading further over the weekend, I would suggest starting in chapter 2 after you get through about half of 1.8. Okay. Yeah, the tilings they're interesting problems, but we're not going to spend too much time on them because we want to get to set theory. Okay, So the first kind of proof is the following, or not, it's not really a new kind of proof, but it's a technique to use. Exhaustive proof, or proof by cases. So these are pretty similar methods or ideas of how to approach a proof, and they both deal when somehow you can divide up the work of doing a proof into some kind of discrete or finite collection of things that you need to prove separately. And the logical idea, especially behind exhaustive proofs, is that if you want to prove a statement like P1 or PK implies Q, this is equivalent to the proposition P1 implies Q and P2 implies Q and so on and so forth, and PK implies Q, and then two parentheses. I can't write another parenthesis. Parenthesis? I can't, okay, whatever. There's another parenthesis at the end here. So what this is saying is essentially this type of proof just means go through the finitely many cases that you have, namely P1 through PK, and show that each of those individually prove the statement that you're interested in. Once again, this is perhaps not so transparent without some examples. So let's do some examples. And I'll need your help for this example. Let's show that there are no perfect cubes less than 1,000 that are the sum of two cubes. Okay, each individually prove it, or all combined they prove it. This is the sort of thing where each individually they prove it. So what do I want to say? Yeah, this is like the kind of problem where you just have to check a couple cases, and either you check that in each case something doesn't work, or you check that in each case something does work, and then thus if you're in any one of those cases, you can conclude Q. So this is kind of a check a number of things. So for instance, these exhaustive proofs are kind of the just brute force. You just do it, right? You just check all the necessary cases. So for instance here, what are all of the perfect cubes that are less than 1,000?
Like 1 through 9.
Yeah, exactly. So all we need to check are, we need to look at 1 cubed, which is equal to 1, or 2 cubed, which is equal to 8, or 3 cubed, which is equal to 27, or 4 cubed, which is equal to 64, or 5 cubed, which is equal to 125, or 6 cubed. This is the first one that I don't know. Can someone tell me what 6 cubed is? Oh, perfect. 216. 7 cubed is equal to 343. 8 cubed is equal to, wait, what is 8 cubed? 512? 9 cubed is equal to 729. Thank you very much for whoever wrote this up. And so now the idea is any number on here equal to a sum of two other numbers? And you kind of just go through and check. So for instance, you could look at every pair and check that they don't add up to the, oh, really? You memorized all of these. That's impressive. So you just can go through and check every single pair in here and say, is the sum of any pair of these equal to another number on this list? And there are going to be finitely many things to check, and none of them are going to work. And then this is a proof that there are no perfect cubes less than 1,000 that are a sum of two cubes. This is why it's called an exhaustive proof, because one, it exhausts all the possibilities, and two, it can possibly be exhausting. Right, so for instance, it's pretty easy to see that 1 plus any of these numbers is not another one on this list, because none of the numbers here differ by 1. Similarly, none of the numbers here differ by 8, because that's just kind of clear. Similarly, none of the numbers differ by 27, because already the gap is too big. Similarly, none of the numbers differ by 64, because once you're here, the gap is already too big, and so on and so forth. So I won't actually write out the totality of this proof, but you can see how proving this statement show that there are no perfect cubes less than 1,000 that are the sum of two cubes just breaks down to check all of the cases. And this is a perfectly acceptable way to prove this sort of statement. Any question here? I admit that this is, I didn't write this proof out very beautifully, so I'm not being a very good role model at this point in time. Maybe I can do a more simple example, one coming straight from the book and one which is suitably nice. For instance, the following. Let's do another example. Prove that n plus 1 cubed is greater than or equal to 3 to the n if n is a positive integer and n is less than or equal to 4. So you see, once again, here we have kind of, there are only so many cases that we even need to check. We need to think about 0, we need to think about 1, we need to think about 2, we need to think about 3, and then we need to think about 4. So we just exhaust all of the possibilities for n, and we just check the fact in every case. So when n is equal to 0, so this is the proof. Well, we check all cases. When n is equal to 0, we have 0 plus 1 cubed is greater than or equal to 3 to the 0, because 3 to the 0 is 1 and 1 cubed is 1. Okay, when n is equal to 1, then we get 2 cubed is equal to 8, which is indeed greater than or equal to 3. When n equals 2, then this is going to be 3 cubed, which is greater than or equal to 9, right? 27 is greater than or equal to 9. When n is equal to 3, then we have 4 cubed, which, good thing someone knows all the cubes. This is 64, which is greater than or equal to 3 cubed, which is 27. And then lastly, when n is equal to 4, then we have 5 cubed, which is equal to 125. This is going to be greater than or equal to 3 to the 4th. That's 81. Okay, so we just did all the cases. What I want to emphasize here is that there are plenty of occasions in mathematics where the solution is just do all of the possibilities, exhaust all of the possible cases that arise. These are perhaps some of the most naive ways of proving a statement, but they're still really valuable. I'll put a little QED here so you know we're done with the proof. Any questions here? When we do induction, will that rid the need for exhaustion, or will there still be times when we need exhaustion? There will still be times when you need exhaustion, right? So induction, and that's a really good example because induction is about proving kind of an infinite sequence of steps, whereas fundamentally proof by exhaustion is like dealing with some proof that only holds true in a finite number of cases. For instance, this statement, n plus 1 cubed greater than or equal to 3 to the n, this doesn't hold when n is greater than 4. Like when we start getting to 6 cubed versus 3 to the 6th, then it kind of switches up. So this sort of statement doesn't generalize to all n. So induction wouldn't work. In fact, I mean, it's not a true statement. So this is, it kind of lives in a complementary zone to induction, perhaps, is a way to think about it. Does that help? Mm-hmm. Yeah, this is an acceptable write-up of this sort of thing. I mean, yeah, if it's a proof by cases, I'm not going to complain if you just write down the cases. In almost every other proof, I'm going to be a stickler about writing out full sentences, but here, you know, I kind of did my best. I mean, how would you grade me on this one? Then I'll do the same to y'all. Okay, let's do a slightly more brainy, well, not brainy. Brainy is the wrong word. A less brute force example. So these were kind of proof by exhaustion. Proof by cases can be a little more subtle than a proof by exhaustion. Oh, actually, my notes say that I should do something else first. Ah, yes. That's very thoughtful. Thanks, y'all. I'll make sure to take that into account when I'm giving y'all your final grades. So I want to briefly discuss without loss of generality. Okay. So without loss of generality essentially appears in proof by cases. So this appears in proof by cases where two or more cases may be superficially different, but no new math occurs. So in this case, so the kind of idea behind proofs where you invoke without loss of generality is you sit down to do a proof and you immediately see that it could translate pretty well into a proof by cases. And then you notice that two of the different cases actually in some way are just exactly the same case. So if that situation occurs, you can say without loss of generality and then just prove one case and not prove the other case. So let's do an example. The example that I want to do is the following problem. Prove that 5x plus 5y is odd when x and y are of opposite parity. Okay. So this problem naturally suggests to me two different cases. What two cases should I be having in my mind when I'm trying to prove this? So I don't want to specify the numbers for X and Y. And I do need, so if I want to, what this statement written slightly differently is if X and Y are of opposite parity, then 5x plus 5y is odd. So in other words, yes. So there are a lot of very good suggestions, but let me hone in on the one that I think I like the best. So if I want to prove this, I want to prove this using direct proof. So I'm going to assume that X and Y are of opposite parity, and then I'm going to show that that forces 5x plus 5y being odd. And now there are many very good suggestions here. For instance, picking numbers for them to try to test out. Same parity and opposite parity is close, and x plus x comma x plus 1 is not quite general enough. But the two cases that I see here are if two things are of opposite parity, one of them needs to be odd and one of them needs to be even. So I would say case 1 is x odd, y even, and case 2 is x even, y odd. I claim that this breaking up of this problem into two cases is precisely the right amount of generality. Because if I show that this result holds in both of these two cases, then I have proven it for everything. Many of the suggestions that y'all brought up would be kind of even further subcases. For instance, x positive and y negative, if you also made them be the opposite parity, then you could prove this result in that case, but then there'd be even more cases, like what if they're of, what if they're both positive, what if they're both negative, things like that. So do we agree that these two cases encapsulate all of the possibilities for x and y being of different parities? Yeah, thank you, by the way, for all of your suggestions. That really makes me happy on this Friday. So thank you so much for joining me in thinking about this. Okay, so the next step is to notice that we could do both of these cases. And indeed, why don't we do case 1? Let's do case 1. So case 1, assume x is odd and y is even. So x is equal to 2k for k in z. Maybe I'll do k1. And sorry, y is odd, 2k k1 plus 1. And y is equal to 2k2 for k2 in z, right? And then we just continue with our proof. Then 5x plus 5y is equal to 5 times 2k1 plus 5, or plus 1, plus 5 times 2k2. And then if we write this out, this is going to be the same thing as 2 times 5k1 plus 5k2 plus 2 plus 1, right? If you mix all the things together. But can't you just prove the second case if the first one is true without loss of generality? Yes, so I want to get exactly, this is precisely where I'm going, although I'm a little slow. So sorry about my, my discussion being a little slow. So thus, 5x plus 5y is odd. So what I did here is I proved one of the cases where this was the case where x was odd and y is even. Now, to do a full case-by-case analysis, or to do a proof by cases, I would then need to prove, well, what happens when x is even and y is odd? But you'll notice that the second case wouldn't actually involve any new math. It would just involve an exchanging of which term was odd and which term was even, right? It would just involve essentially like a relabeling, but the calculation would look exactly the same. I would have 5x plus 5y, and then I'd have it's equal to 5 times 2k2 plus 5 times 2k1 plus 1. Do you agree that case 2 doesn't involve any different math than case 1 does? Right. So in this situation, our first approach was to break it up into cases, but then it appears that the two cases don't actually involve any different math. In this situation, we use without loss of generality, and then we don't need to prove the two cases because they're not actually different. So in this case, I would just say, so my full proof of this would be without loss of generality, assume x is odd and y is even. And then I would repeat this proof right below, and then I'd finish it with a box. Hopefully this isn't getting too messy or confusing. I just want to introduce without loss of generality as a way of not proving redundant cases. Any questions on this? No? Okay. So let's do this kind of further, more challenging example. So more challenging. Let's prove the triangle inequality. Prove that for x and y in R here being the real numbers, absolute value of x plus absolute value of y is greater than or equal to x plus y. Okay. I claim that there are either 6 cases or 4 cases. What I would claim is that first there appear to be 6 cases, but then upon further inspection and using without loss of generality, there are actually going to be 4 cases that we need to examine. Could someone tell me which cases appear? Or at least tell me one of the cases. I really liked your guesses for the last one, so I would encourage some more guesses. Okay, here's a first hint. Where does the behavior of absolute value change? Yes, x being negative and y being positive. Yes, excellent suggestions. So the idea is that absolute value is a function which has very reasonable behavior when x is greater than or equal to 0, and very reasonable behavior when x is less than 0, but there's a change in the behavior at 0. So if there are cases to be done involving absolute values, the cases should involve whether the different variables are positive or negative. So here are my cases. X greater than or equal to 0 and y greater than or equal to 0 is a very nice first case. And then case 2, is kind of the opposite. X less than or equal to 0 and y less than or equal to 0 would be another good case. And then there are going to be a number of cases. Yeah, so this is a very good point that y'all are starting to hone in on. Let's do the following case. Well, I need a case 3 where I have, say, x greater than or equal to 0 and y less than 0. Here's a case. And then I probably want to break up even further depending on the magnitude of x and y. So for instance, absolute value of x is greater than or equal to absolute value of y. So on the number line, this would look something like this. If I have 0 here, I want to think about some cases where x is a big positive number and y is a small negative number. And I also can do, say, case 4. Well, I'm going to handle the cases where x and y can be 0. Oh, shoot. This should be less than 0. Sorry, less than 0. I'm just going to throw the ability to be equal to 0 into the positive case. And technically, this is just for all x and y in R, even if it doesn't make sense as a triangle, if it makes sense as a degenerate triangle, so to speak. So I do want to emphasize that the triangle inequality should allow for x and y to be 0, even though then it doesn't make sense as a triangle. Okay, but if we have this picture, then we could also have a different picture where the x and the y are reversed. So I could have y greater than or equal to 0, x less than 0, and then I could have the absolute value of y be greater than or equal to the absolute value of x. So this is the picture where I have y way out here, and I have x down here. And then I have 2 more cases. Case 5, which will be this sort of picture, where I have x being a small positive number and y being a large negative number, x greater than or equal to 0, y less than 0, and the magnitude of x is, say, less than the magnitude of y. And similarly, case 6, I could have y greater than or equal to 0, x less than 0, and the magnitude of y less than the magnitude of x. So that would be this picture, 0, y, x. Yes, this is an excellent point, Shreya, that you have. So I wrote out all of these cases because these are all of the different ways that I want to break down this problem. And indeed, every single possible pair of numbers will fit into one of these cases, right? If you give me any 2 possible real numbers, I will be able to fit them into one of these 6 cases. But you'll notice that I drew exactly the same picture for cases 3 and 4 and for cases 5 and 6. All I did was switch the labeling. So that's a hint that these 2 are going to be the same using without loss of generality, cases 3 and 4. And similarly, cases 5 and 6 are going to be the same without loss of generality. Do y'all kind of see how how first I lay out all the possible cases that I need to solve the problem, but then I examine which cases don't actually involve any new math, and then I can reduce the number of proofs that I have to do using without loss of generality. Great. Any further questions about what I've done here? Another thing, these pictures that I drew are important. This is advice that I give to all of my calc students and all of my students is you should try to draw or sketch in math as much as you can. Our spatial reasoning is very strong, and our ability to manipulate abstract formulas is pretty weak as humans. So sketching and drawing out different cases really helps our mathematical intuition. I'm not saying that this is a necessary part of the proof, but I encourage mathematical sketching and drawing. It's very helpful to me. Okay, so if y'all are happy with how I approached breaking this problem into cases, then now what remains is to prove it. So proof. We use proof by cases. Case 1. Assume x is greater than or equal to 0 and y is greater than or equal to 0. Then absolute value of x plus absolute value of y. Well, if I have numbers that are greater than or equal to 0, what does the absolute value actually do? Doesn't change anything. So if both of these are positive, absolute value of x plus absolute value of y is just equal to x plus y. And what about absolute value of x plus y? Well, if x and y are both positive, then their sum is positive or greater than or equal to 0. So also this doesn't change. So this is also equal to x plus y. So this settles this case because when everything is positive, then they're just equal. This and case 2 are easy. Case 2, assume x is less than 0 and y is less than 0. Then what is absolute value of x plus absolute value of y? What do the absolute value things do to negative numbers?
Make them positive.
Yes, they make them positive, and they do so by multiplying by a -1, right? What does the absolute value of -2 do? Well, it multiplies -2 by -1, and then you get 2. Yeah, so the idea is it negates negative numbers, but the precise way to think about that is you multiply by a -1. So in particular, this will be equal to -x plus -y, which is equal to -x plus y. Now, remember, x plus y is a negative number, so absolute value sign of x plus y is the same thing as just multiplying x plus y by a -1. So in this case, these are the chain of steps that lead us to see that these are actually equal. Any questions thus far? Okay, let's do case 3. So we're going to do x greater than or equal to 0, y less than 0. And without loss of generality, we're going to assume that the absolute value or the magnitude of x is greater than or equal to the magnitude of y. And so I'm going to draw a little picture just to help us. This looks like this. 0, x is way over here, and y is this small negative number out here. Okay, so now we write absolute value of x plus absolute value of y. And what is this equal to? Yeah, I'll write this as being equal to x plus a negative y, or the same thing as x minus y. And now I'm going to use my, okay. So I've got an expression for one of my terms. How about let's just try to understand what's going on with x plus y. What is x plus y? Well, here's a question. X plus y, is this going to be a positive number or a negative number? That's what we have to first figure out in order to see what the absolute value does. Right, x plus y is a positive number because of our assumption, or it's greater than or equal to 0. Thus, x plus y, absolute value, is just equal to x plus y. And now I can compare. Now, x minus y is greater than or equal to x, since y is a negative number, which is greater than or equal to x plus y, because once again, y is a negative number. You can kind of see it here. Here is x minus y, and here is x plus y. So the way that I compare them is I compare them against x. X minus y is bigger because y is a negative number, and x plus y is a little smaller because y is a negative number. So absolute value of x plus absolute value of y, which is equal to x minus y, is greater than or equal to x, greater than or equal to x plus y, which is equal to absolute value of x plus y. Here's another helpful mathematical tool that we use, is if you're trying to compare two numbers in absolute value, it's often very helpful to find some intermediate value that you can compare each of them to. Any questions here, or is this more or less straightforward? Should I do the last one? How I got negative y. You mean in this step right here? I get a negative y because I assumed that y is less than 0, and how absolute value, so maybe I'll write it as follows. Here's the way to define absolute value. Absolute value of x is a piecewise defined function, which is equal to x when x is greater than or equal to 0, and it's equal to -1 times x when x is less than 0. So whenever my input to the function is less than 0, the absolute value does the same thing as multiplying by a -1. So here I assume that my y was less than 0, which immediately, or here, I assume my y is less than 0, which says the application of absolute value is the same thing as multiplying by a -1. Does that help? Okay, let's do the last case, case 4. So here we assume, so this is what used to be case 5, but now it's case 4 after doing without loss of generality. We assume that x is greater than or equal to 0, y is less than 0, and absolute value of x is less than absolute value of y. So here the picture is going to be something like this. 0, x is some small positive number, and y is some large magnitude negative number. And here we repeat the same procedure. Absolute value of x plus absolute value of y is going to be equal to what?
Is it x plus minus y?
Yep, this is always the same. This is just going to be x plus minus y. Let's see. So x plus minus y is going to be like way up here, right? X plus minus y. And then we also have to examine x plus y. Now, what is x plus y a positive number or a negative number? Yeah, exactly. Now x plus y is a negative number based on our assumption. So this is going to be equal to negative x plus y, because that's how absolute value signs work. And in pictures, negative x plus y, or the absolute value of x plus y. So here is x plus y. It's something like this, right? X plus y. And then the absolute value of x plus y is over here. Do you kind of see how that works? Okay, so we want to find a nice way to compare these two numbers. So here's my following claim. I claim that absolute value of x plus absolute value of y is equal to x plus negative y. This is greater than or equal to negative y, right? Negative y lives like right in here. So negative y is some positive number, and then if I add the small positive number x to it, I go up a little bit. And similarly, negative y is going to be greater in magnitude than negative x plus y, which is greater than or equal to negative x plus negative y, because this is now some positive number, but now I'm subtracting off a small negative number from it, right? I took negative y, and I am subtracting a positive number. So I move a little bit to the left. But this thing is exactly equal to absolute value of x plus y. So here, once again, I get absolute value of x plus absolute value of y is greater than or equal to absolute value of x plus y. Nice. The pictures really help in this case, at least for me, to kind of examine how I can compare the different numbers. And then this is QED. I did all the cases. Here I should have mentioned without loss of generality. Without loss of generality, absolute value of x is less than absolute value of y. So I can roll two cases up into one. Any questions? No? Well then, I hope that y'all have a wonderful Friday and a great weekend, and thanks for being so vocal in the chat today. Made me happy.
Thank you.
Yep, have a lovely weekend, everyone. Yeah, absolutely. Question 15, prove that if x is an irrational number and x is greater than 0, then square root of x is also irrational. Okay. So what is your idea for approaching this proof?
So basically, I thought that since we're dealing with irrational, it would make most sense to do contrapositive, because then we could deal with rational numbers.
Mm-hmm.
I guess my question was, if we negate the first part of it, would we get x is rational or x is less than or equal to 0?
If you negate the first part of it, yes, that's what you'd get. You get either x is rational or x is less than or equal to 0. My taste for this problem would be contradiction, because I don't want to deal with that or in the beginning. So for me, a nice collection of premises to work with would be x is irrational, x is greater than 0, and square root of x is rational.
I'm sorry, can you repeat where you got that? So that's from contradiction?
Yeah, this is from contradiction. So here you're trying to show P implies Q.
Mm-hmm.
And so how do we, if we're trying to prove this, so prove P implies Q, how do proofs by contradiction proceed?
We show that, or we assume P implies not Q, and then show that that leads to a contradiction, right?
So it's not quite that. What we do is we assume the negation. So the way that we do a proof by contradiction is if we want to prove a statement, we assume the negation and show that that leads to a contradiction. But what's the negation of P implies Q?
So it would be the negation of not P or Q.
Uh-huh, great. And then what is this?
So that would be P and not Q.
Yes. So when you're
Okay.
trying to prove a P implies Q and you decide to use proof by contradiction, what you assume is P and not Q.
Mm-hmm.
So I assumed P and I assumed not Q.
Okay, I see.
Mm-hmm.
So to show that X is irrational, would we just say that it can't be written as A over B?
So here, I actually don't want to play with the X is irrational part. I want to play with the square root of X is rational part.
Okay.
So you're not incorrect, right? X being irrational means that it can never be written as a fraction A over B, where A and B are integers and B is non-zero. That is absolutely correct.
Mm-hmm.
But one thing that I've kind of emphasized is that it's much easier to play with things that, like, this was your instinct behind contrapositive, right? You know that it's easier to work with rational things than it is to work with irrational things.
Right.
So, and we don't need to prove that X is irrational. That's part of our assumption.
Okay. So we're just gonna say that square root of X is rational and then show that as like an A over B.
Right, exactly. So let's do this exactly. So since square root of X is rational, square root of X is equal to A over B, A, B in Z, and B not equal to 0. Okay,
Mm-hmm.
what next?
So then I would square both sides and you
Yeah,
get X is A squared over B squared, which
that's it.
is clearly a rational number.
Yes, so X is rational. But X was assumed to be irrational. Now do you see the
Okay.
contradiction that we have produced?
Yes.
Now we have R of X and not R of X.
Okay, that makes more sense. I think my problem was like trying to mess with the hypothesis, like P instead of
Mm-hmm.
Q.
Yeah.
And I didn't think of contradiction either. I was thinking it had to be contrapositive.
And these things take time. So, we're going to be doing a lot of proofs for the rest of the semester, and it takes time to gain a little bit of experience for when to use contrapositive and when to use contradiction.
All right, cool. Well, thank you so much. Hope you have a good weekend.
Yeah, you too.
Bye.
Bye.